Okay, so let's start. Thank you very much for coming to another seminar. Today it's on Thursday, not on Friday, as usual. It's still working. And today we have Roman, and it's a visitor researcher. So Victor will introduce him a bit. So thank you very much.
Thanks, Makhnenko. So we have the pleasure to have Roman Makhnenko visiting us. He's in a sabbatical, so he will be here for a while. If you have interest to talk with him, you will find him in a while. We met in long time ago, 13 years ago, when we were both postdocs at EPFL, and now he became professor at University of Illinois in Urbana-Champaign. Now he got the tenure, so he's associate professor. And we have been keeping collaborating since then. We complement each other. He works mainly in the lab. I do modeling, but I need him to know what should I put in my models. We have been working in several topics: geological carbon storage, geothermal energy, nuclear waste disposal, and more recently on hydrogen storage. And the presentation of today will be on this topic. So, Roman, please, you have the floor.
Yeah, thank you very much, Victor and Makhnenko, for organizing. So, pleasure to be here. And yeah, I mainly came to improve my cycling skills, but also good to be at the institute. So this is a kind of a new topic we're working on. I hope my slides don't look that bad. I'm at the civil engineering department, University of Illinois. We're ranked #1, by the way, in the US in terms of civil engineering. And I created Rock Mechanics Group. This is my logo. And I also have affiliation with the Institute of Sustainability and National Center for Supercomputing Applications. This work was mainly done by two of my students that I will show. Hyunbin Kim is now a postdoc, and then John Brookbank is continuing on testing rock with hydrogen. And the title is kind of very ambitious, but I'll try to explain where it comes from. So a little bit of background, as Victor has mentioned, we were both postdocs at the PFL. That was 13 years ago. I got my master and PhD from the University of Minnesota in the United States. There still sometimes could be snow there in May, so snow is something you can see in the mountains here, but very rarely. Yeah, so we had, and everywhere where I've been, basically, I was trying to work on developing new systems for testing rock, and usually in contact with different fluids and at high pressure, sometimes high temperature. And eventually moved to central Illinois. So this is our beautiful campus, Urbana-Champaign. And yeah, we have two labs. This is my rock mechanics lab, where we have a lot of equipment where we're trying to represent the behavior of rock-like materials under the conditions of underground storage. So we look at what is called geoenergy systems. We work on some petroleum applications, but mainly things that are related to storing the waste from energy production, like nuclear waste disposal or CO2 storage. Yeah, recently also started working on hydrogen storage. And there are different formations that are involved there. So I will try to explain what we do in terms of hydrogen storage in more detail. This is usually a slide we're showing to some kids who come for summer schools. Basically, renewable energy is hopefully growing everywhere. So we're trying to use less of the fossil fuels, more of the renewables. Sometimes it's just forced by the political situation, economic situation, but hopefully a lot of times it's motivated by our desire to produce green energy rather than emitting a lot of greenhouse gases. And Illinois, actually, where I now come from, is one of the best states. We're trying to kind of deviate from fossil fuels and use more of the renewables there. We're second in the nation by producing the wind energy. We're building some solar farms, and there is an initiative to have solar panels in every house. And we're also leading the initiative on growing some special grass that allows to create biofuel and ethanol. So, and you know, in the US, these plots, they actually have many significant fluctuations. If you look at the whole picture, every 4 years, how we approach renewables and fossil fuels is changing. Somehow it coincides very much with the presidential elections. So then I spent some time preparing this slide. I think so Spain is working hard in also moving to some of the types of the renewables. There are some now plants where hydrogen is produced and solar farms, wind farms, and the fraction of the renewables is increasing. I believe the last report I read was 43% of energy generation, and maybe it's overestimated, but you know, now Spain is continuously producing more that it consumes, so it can actually also sell some energy. And I think in terms of renewables, it's one of the best in Europe, at least that's what I read yesterday preparing these slides. And now the issue with the production of the renewable energies, especially you know solar and wind, is that, or solar, we all understand has fluctuations on a daily basis, right? Because then it's a dark time, it's at nighttime sometimes. But for the wind, for example, there are seasons, and it depends, of course, where you're at. I think this is probably from northern Germany. There are seasons when you have, you know, strong winds and you produce terawatts of electricity. And there are low seasons when you produce very little. So let's say if this is somewhere here is our threshold. It means that we need to somehow store when we have a surplus electricity production, and then we need to use what we have stored during these low seasons. And there are different approaches to that. There are approaches, you know, that are based on injecting, let's say, even air underground. So we have electricity. We can, you know, use then it to convert it to some fluids to high pressure and then use it later. Or, for example, during the peak times with surplus electricity, we can pump the water somewhere, you know, uphill, up the mountain, and then when it will be running downhill, it can produce electricity. Or we can somehow, you know, create big batteries and store it in the batteries until we need it. This is very expensive technique. So basically, a lot of times, let's say in Texas or Colorado, when we're producing too much of the renewable energy, they actually shut off the windmills. So like 30 to 40% of them, there are days when they're not working because they produce too much, and they have been days where they were paying customers, and so not the customers were paying for electricity, but they were paying the customers to take more from the grid to reduce the loading on the grid. So it was too much produced. So somehow we need to store it and then use it later. There are different approaches, and the one that I want to talk about is related to high production of hydrogen. So you can have these cells, where so the reaction is known. If you have, you know, high voltage going through water, it can separate oxygen from hydrogen. Like we have these toys that we show to, you know, when we go to schools to talk about renewable energy, and we have like a small car that is running on hydrogen, or we can produce hydrogen. So when we have a surplus electricity, we can separate oxygen from hydrogen, and hydrogen can be used as a fuel. Actually, buses in where I live in Champaign and Urbana, they run on hydrogen. It's used in the chemical production, in transportation, and so there is a reaction that separates oxygen from hydrogen. But when we bring oxygen again from atmosphere and hydrogen from a tank, they go through like electrodes, and then they mix. They can produce electricity. Or that can be converted to mechanical moments, and then actually in this case you would expel water, and they say this water would be so clean that you can drink it. So the cars that ideally would run on hydrogen, so you use hydrogen and oxygen, and then you should produce clean water on this. So I don't have a big, so we have small cars. I don't not yet making much to buy a big one, but maybe in a few years I'll update you on this. And of course, in terms of hydrogen, like where do we get it from? We know that there is natural hydrogen in a lot of locations everywhere, basically in the world. So there are some minerals that under certain conditions, high pressure, temperature above 200 degrees Celsius, like olivine, when they react with water, they do produce hydrogen. So this natural hydrogen can be extracted, and we're now trying to kind of accelerate and promote it in the United States to use this hydrogen as a fuel. But we are talking about slightly different thing, right? When we produce hydrogen on the surface, because we use the renewable energy resources that sometimes, they have too much. Where can we store it? And we have the experience, not only, of course, in the US, but Canada, Europe, Germany, where hydrogen has been stored in salt caverns. So basically, you could inject water to wash away some of the salt and then actually extract this water. And it's supposed to be very salty, but sometimes they put it in the ocean, sometimes they just put it somewhere else. And then so it creates a reservoir in this salt cavern, and then you can inject hydrogen. And if you do it right, then you can come back to it, let's say in half a year or in a few months when you have a low electricity production, and then you can use it. There are a lot of issues associated with that, but one of the big issues is that if we look at the location of the major salt domes, right? So this is Texas, New Mexico. We know that there are like 2 national labs that are sitting on top of here and working on it. So somewhere, here, Illinois is here. We are the second state in terms of producing renewable energy, but we have nowhere to store it. I've seen some presentations when people were saying, yeah, okay, we will transfer hydrogen to New Mexico, and then when we need it, we transfer it back, but it takes some time. So another idea is to actually try to store hydrogen in the formations that are available almost everywhere, saline aquifers. So we have freshwater aquifers close to the surface, but going deeper, the water becomes undrinkable, but it still saturates everything. And of course, you have Dr. Villarasa here, who is working on CO2 storage in saline aquifers. We also do it in Illinois. But in this case, we discussed potential hydrogen storage in saline aquifers. So we would inject hydrogen in there. And we also need to have some cushion gas that will be pushing it. And then when we need to come back, when we need to extract it, we should be able to get back. And the big question is, of course, when you get back to the reservoir, will you have hydrogen still there? How it's going to flow there, how it's going to affect the rock in terms of there could be some chemical effect, as well as it could leak through the capital. And I have been working on CO2 storage now for some number of years. So we were exploring, of course, how safely we can store CO2 underground. And now a similar challenge comes with hydrogen, but the problem is with hydrogen is that first a lot of CO2 under this high temperature and pressure condition dissolves in brine, in saline water. With hydrogen, it's significantly less. Let's say that it's the temperature and pressure that we're working with, it would be like 30% of CO2 being injected CO2 being dissolved versus 2% of hydrogen. And the second thing is that hydrogen is just a very nasty gas. It's so I'm showing some of the things here. Maybe you've heard of this. There are some documentaries about it. It's flammable. There are sometimes you get in the news like truck in Italy transferring hydrogen got on fire. This was a famous catastrophe, unfortunate. But basically the viscosity is quite small. The density is quite small. Small viscosity means that it's leaking everywhere. It's very difficult to build a system where it's not leaking. And in terms of, just dealing with it, so we've seen some modeling where basically geomechanical models that used to be working for CO2 storage, they just changed this viscosity and density of the hydrogen and they put it in the model. We don't think it's going to work like this because, again, the whole fluid dynamics could be different, and that's what we wanted to explore. We also acknowledge that actually the conditions that we're trying to look at is this mainly this purple triangle, which says that hydrogen is in a supercritical state. So it still looks like a gas and actually doesn't change much of these properties. But yeah, we need to remember that it's a supercritical fluid. So, and when this topic came, and basically in the US, the motivation, it's called 1 for 1 for 1. So 1 kilogram of hydrogen in 1 decade should cost $1. Now it costs around 5. And that was the initiative of Biden administration. Last January, we got a new administration, and a lot of these initiatives were stopped. There was no funding, and they even closed the hydrogen hubs that were already created. And unfortunately, some other countries and companies working in other countries also decided to follow this. So 2026 is the year when this is kind of declining, but now we will see with other fuels costing a lot, maybe the perspective will change. So this topic was of interest in the United States, but a lot of labs were hesitant to start working on it because, again, exactly of this thing, they're scared that they're going to have some fire. So we're not scared, hopefully. So we have a system actually where we calibrated the fire alarm or hydrogen sensor so that if we exceed a certain concentration of hydrogen in the air, there should be an alarm, fire extinguisher, and hopefully the facilities manager and then firefighters will come and help. Hopefully it will never happen though. So we built the lab where we're working with hydrogen. There are a few devices like this, core flooding, where we can saturate the rock. So we subject it to some confining pressure that represents in situ conditions. We saturate it, and then we can inject hydrogen on top of the fluid saturated rock. Then we also have systems where we can actually measure the mechanical response due to hydrogen injection. We can also look at what happens to the specimens, how their porosity and how the pore size distribution and the morphology of the pores is changing upon hydrogen injection. So we started working on this topic 3 years ago. But actually, this is the first time I'm really presenting on it, not at my group meeting. So hopefully it looks solid. And also I need to acknowledge that our most recent project is sponsored by BP, so I can put it in my report that I presented on it. So a few things that we're interested in. First thing is basically, okay, if we inject hydrogen in a certain porous rock, let's say in December, and then we know that we have low production from the windmills in March. When we come back to the same reservoir, how much hydrogen can we recover, and can we efficiently recover? And that also comes to the question where, so it's a question of two fluids coexisting in the pore space. So now we have brine, or actually there will be 3 fluids, but let's say close to the caprock we have 2. We'll have wetting fluid, saline water, brine, and we'll have non-wetting fluid, hydrogen. And when there are more than one fluid in the pore space, though, these 2 fluids are competing, and basically they significantly reduce the permeability, the ability to for the fluids to flow inside. So sometimes we plot it as what's called relative permeability curves, where basically if we are below a certain degree of saturation for each fluid, it shows that it has a very, very hard time to flow, and sometimes it stops flowing. So you can have 2 fluids, but like one of them, let's say water, would still have some flow, very small, and hydrogen might have nothing somewhere here. So understanding these curves and also like putting them in some models is important, measuring them. So that was one of the goals of the techniques that we were trying to establish. So, and actually we had a project when we established the lab, from the Department of Transportation, that we're looking at the possibility to store hydrogen in the Illinois basin. So we're sitting on top of a number of different very interesting formations, but some of them allow the conditions for underground storage. For example, one of the best monitored CO2 storage projects in the world is happening in central Illinois, where we inject in Mount Simon sandstone, and Eau Claire shale is the cap rock for CO2 storage. We also have some basement rock here where some seismicity happens. For hydrogen storage, they were aiming at the sandstone, or actually it's called Ironton Galesville Formation. We call it sandstone, but there are some shell inclusions there. So, we extract these specimens, they come from a very similar depth. You see 7 feet, it's feet. So 1 foot is around 31 centimeter, depending on your shoe size. So we extract these cores from the borehole, and these kind of sandstone-like cores, they still have some inclusions of clay, but there are also cores that are shaly. So basically, some of the layers here can serve as the caprock, as the material that provides barrier for hydrogen leakage, and some of them can serve as a host. So we were looking into this formation, trying to understand if it would be good for hydrogen storage. And kind of a common approach is that we discussed here at the group meeting 2 hours ago was that you can measure the pore size distribution or retention properties of the materials and then interpret them in terms of this relative permeability. So in fact, you don't need to, or in some cases for some kind of ideal materials, you don't need to run those tests where you need to build a lab, you need to have people who are checking the safety of the lab every 2 weeks, you need to meet all these criteria, you work under high pressure, you saturate the rock, so you can run some simple tests to kind of predict what happens there. And of course, we also can look at the existing data for even, this is mainly sandstones, it's quite sparse, so there these relative permeability curves, they very much depend on the material and the testing conditions, so it's kind of difficult to choose which one would represent how our material might behave. There is also, now we use some statistical methods where we try to say, okay, some of these parameters like relative permeability or residual degree of saturation, can they be correlated with some of the index properties of the rock that we measure, for example, permeability or pore size distribution or the dominant pore size. And again, we see that the data is quite sparse, so we cannot really make good assumptions there. So we need to directly measure basically each look into each material. And we developed a technique where we make these two fluids flow through the rock. We then measure the degree of saturation by seeing how the compressibility of the rock is changing, because hydrogen is much more compressible than brine. So we see that the compressibility of the material is changing, and we can judge, like we can calibrate it. We ran some tests to see how the mixture of water and hydrogen is changing depending on the fraction of hydrogen in water and depending on the pressure and also temperature. So we can calibrate this technique, and then we can get this relative permeability curves. We did it first for some kind of ideal material, almost pure quartz arenite, Berea sandstone, where we see that there is some slight dependence of these curves on the applied confinement. And an interesting thing that we saw was that there is some hysteresis, but only for the first and second injection cycle. So if we look at this representation of relative permeability, we inject, then when we inject water back, we don't get back to the initial condition, but actually we had like third and fourth cycle where then they were following this curve. So some hydrogen, we believe, is being trapped after first injection, but then we can actually recover most of it for this porous sandstone. And then we could try to make a prediction for this Ironton Galesville, for this natural rock potential host for hydrogen storage. And I just wanted to show, didn't want to go too much into detail, but the prediction versus the real measurement is quite different. So when we start working with heterogeneous materials and anisotropic materials, this pore scale estimation is not very good predictor of what you will have in terms of the flow properties of the material. So we think that, we need to go and directly measure it. So this was one of our main conclusions. Now, I wanted to highlight, I know that it's a 30-minute seminar. We started at around 05, right? So I wanted to highlight the things that we're currently working related to the breakthrough. So we're talking about the caprock now. We want the caprock to be a tight material where hydrogen cannot actually flow through. So it will provide the natural barrier for hydrogen storage. And we use techniques similar to what we use for CO2 storage, where we basically represent this hydrogen injection step by step, and we try to see when we have the breakthrough, the flow of the second non-wetting fluid. We have some kind of very scattered results so far, and we use different methods that usually are recommended for this. And we acknowledge that hydrogen is, again, such a nasty fluid that it could be not only flowing through the rock, but leaking in the system. So we have a lot of noise, and sometimes it's difficult to recognize where this breakthrough is happening. And currently, so the method that we're trying to use, the method that we're trying to use, is based on the mechanical response of the material, where we see that when hydrogen really breaks through, the material starts deforming. So when the hydrogen just enters the material, and then when it breaks through. So we base our estimation of this breakthrough on the coupled hydromechanical response of the material. This is the technique that we're currently calibrating. And again, if we look at the correlation of kind of predictions from indirect methods where it should occur versus the direct measurements, the difference is like 3 times. So we would really be underestimating the breakthrough pressure if we use indirect porosimetry based methods versus the direct measurements. But these methods are they take a lot of time to fully saturate the rock, and then you see each test could be a few weeks long. And of course, all of these have been done now so far for the intact rock. We have experience working with CO2 where we know that CO2 breakthrough pressure is significantly smaller if the material is fractured or just kind of remolded, restructured. The intrinsic permeability of the material increases significantly, and the breakthrough pressure decreases. So the most dangerous part should be fractures in this cap rock, and this is the thing that we will be looking at in the near future. One more thing that I wanted to highlight is the potential chemical effects. So some of the things didn't transfer well, but so we reviewed the literature. It was saying that hydrogen should have very small chemical effect because hydrogen mixed with water doesn't really create an aggressive fluid. When we were testing some limestones, we were collecting the e-fluid, so the fluid that comes out of the specimen. So we had some, original specimens, and then we had a few cycles of injection and imbibition, and we've noticed that we are changing some chemistry of the pore fluid, and especially the main thing that we keep collecting upon injection in calcite-rich rock is calcite. So the injection of hydrogen is dissolving some calcite. On the other side, we look at the mechanical response of the material before and after hydrogen injection, and we noticed that actually for some of the material, or actually 2 materials that we had, one was there should be dolomite. There is some dolomitic inclusions here, but it's called shale, and then the limestone. We noticed that actually the porosity after hydrogen flow through experiments has decreased, and some of the mechanical response got slightly stiffer. So instead of just having pure dissolution, there could be some precipitation of calcite too, as well as what is called calcite expansion due to the reaction with hydrogen. So this is still something to be explored from different perspectives, and we're trying to collaborate with Victor's group also to look into it, but there is some interesting chemical effect happening here. And one last thing that I wanted to mention is that also with hydrogen, it is known that there is some biological reactions that could be produced. So, and there was some research showing that these biological reactions could be actually quite severe in the way that if we look, for example, at those contact angles that determine the multi-phase flow, they could change significantly due to the bacteria growth and like what bacteria does to the rock, and it changes the mineralogy of the material. So there is some coupled biochemical effect that could be happening there. And this is another thing that when we collect this fluid coming out of the specimen, that we will try to understand. So then, we talk about oftentimes in the underground storage about coupled processes. So in terms of hydrogen, we're looking at the hydromechanical interaction. That's just what happens when we inject hydrogen in the subsurface. There could be some thermal effect because the hydrogen would be injected at lower temperature than the reservoir, but it might be not that important because we usually talk about the depths of a few hundred meters, maybe 1.5 kilometers at most. We see that there is some chemical effect, and then we acknowledge that, or some of the labs and in natural occurrences, there is also biological effect. So we have been kind of progressing, going from highly porous materials that represent the reservoir and seeing some chemical effect there and two-phase flow to very tight rock, which each specimen could take a few months to be tested because of the small porosity and small pore sizes, but looking how they could be good seals for hydrogen storage. So this is kind of research in progress that I wanted to share. And of course, proper understanding of this underground storage and safety of the operations would depend on how we get the log data from the field, how we know the field parameters, how we characterize it in the lab, how we can see what would be the chemical effect and the hydromechanical, and even building some models, also collecting some data to build some large-scale 3D models to predict what happens. So this is my last slide. Thank you very much.
Thank you very much, Juan. Any questions?
Thanks, Martin. So you mentioned the concept of hysteresis and cyclic injection in terms of the saturation, but what is the implications for injection pressure? If the residual saturation increases after the first injection, then what would be the injection pressure changes in the next cycles?
We don't change this condition in the. So the question was, if we observe some hysteresis, that's true in tests, even with Berea sandstone, and then with that other sandstone that we tested, the natural material. And the question was if the injection pressure would change because we have some hydrogen trapped.
Yeah, so it has a direct implication for the saturation, for the amount of hydrogen that we can inject or recover.
Right.
But how about in terms of the pressure?
Or I don't know how they're going to do it in the field. I assume, at least in the lab, we try to maintain the same pressure because we try to compare the conditions when we have multiple injection. Of course, we want to have all the conditions to be preserved the same to be able to properly compare it. If they're going to adjust it for the field operation, yeah, probably yes, but I think there are also certain limits, of course, that
the saturation is something like 15%, right? According to the
or here, so for Berea sandstone, I think we went to almost 90. So we need to look at this part, right? And then for that other material, I'm not showing the curve. I can look at it, and I think it's around 70-something% of water saturation after the. So when you take hydrogen off, right? So there will be 20-something% of hydrogen trapped. Now, I'm not showing the data for limestones for the reason is that actually the chemical effect that we observed was in a way that these curves went above this point. So we cannot really compare them to the permeability that was there before because the intrinsic permeability of the material has changed. So we cannot really properly interpret, at least for now, how much hydrogen was trapped. Okay, because there is a combined chemical and hydromechanical effect. In terms of what we would do in the field if we get some hydrogen trapped, do you need to have higher, you say, injection pressure to recover more? Is that your question?
It won't be recovered, right? Or is it? It's a hydrogen permanently stored in the pores as a residual.
Yeah, it could be trapped, right? And of course, this is still something that we need to look at and maybe better using X-ray CT scanning to see how exactly it is trapped, can it be recovered, right? So we know that, for example, with CO2, when it's being trapped, usually even when we have multiple injection and drainage imbibition cycles, it's getting into smaller pores, and it's very difficult then to recover it, right? But in terms of CO2 storage, it's actually a good thing because you want it to stay there. For hydrogen, it's the opposite. You want to recover as much as possible. When we talked to the people from industry, because that was actually industry-based project, they were very happy with 90 and even 75% recovery. And of course, we're not considering things here like, there's a natural there's a natural brine flow in the reservoir, right? There's some other things happening there. So this is kind of an ideal laboratory condition. I think in the reality, you would recover significantly less, that hydrogen could be flowing away within these few months or a few weeks that you store it there. You could be recovering significantly less. So this is still something to look at. Okay. Victor?
So regarding the geochemical effects that you see, so do you see them in the hydrogen or in the pore water that is flowing upwards?
Yeah, we look at the pore fluid. So it's and in fact, we don't. So when we collect this pore fluid, it's a mixture of hydrogen and brine. But when we send it for testing, we need to release the pressure. So we go outside. Actually, this is our safe method of releasing hydrogen. We release the hydrogen, so it remains to be just the brine. But when hydrogen and brine were flowing through the rock, they were washing away some of the minerals. So we see some increased.
Similar experiment just with the flow of deionized water.
Yes, so that's actually what we did. So we have some reference case, how much deionized water is. So there is actually some, this is deionized water, you see. This is how much calcite was there, milligrams per liter, less than 1. And then when we had a few flow tests, I don't know why we're showing 5th, we had significantly more. So we believe that some of it is being washed away, but at the same time, you see I'm showing these plots, and actually, I mean, okay, pore size, there's a lot of statistics here we need to measure. We need to probably run more tests. This is like maybe 3 tests for pristine versus treated here. But we definitely see, we ran 2 or 3 of those where the material response gets stiffer. So there is something happening there that it's, because if it would be just the dissolution, it increases the porosity of the rock. That usually means that the rock gets more compliant. But in this case,
if you have porosity increase, this means that you have some precipitation, and sometimes the precipitates have larger volumes than the original mineral.
Yeah, and it also changes the pore structure, right? So for example, you precipitate, you can create some occluded pores that we don't see.
But then in terms of permeability, with this decrease in porosity, is the permeability increasing?
Yeah, I think that it's slightly decreased, right? But it was like 10%. So 10% for us is still within probably an accuracy of the measurement. So we cannot make like, very conclusive statement here. But it definitely, like, with CO2, for sure, we see that some of these limestones, it could be like 50% increase in permeability. With hydrogen, it was definitely not increasing and maybe even slightly decreasing.
How about the location? And this processes is for representative of the whole sample, or it's for?
Yeah, that's a good question. As I mentioned, we took a few samples from the specimen, right, that we tested. Maybe like this data is average for 3 specimens. So yeah, usually you need more. And of course, also you can expect, I think that this was not the case here, but again, I'm comparing to the projects that I've been working on for much longer than hydrogen CO2 storage. Then you have some difference where close to the injection versus the downstream part of the specimen. So this is still something that we need to look at. But yeah, thank you. Very, very good question. Okay. Anything else? Okay.
So we can leave it here. Thank you very much again.
Thank you.